Okay, this is lesson 1.7b. This is stretches and compressions. Just like reflections, we can stretch and compress both horizontally and vertically. The types that you've seen up to this point in terms of stretches and compressions were only vertical, and it was with a parabola. So let's refresh what that looks like. If we had a parabola, say this is the shape of our standard parabola, what would a vertical stretch look like? Well, it would just be skinnier, right? Because the points would go vertical faster. So then what would a vertical compression look like? Well, it would be flatter and wider. So it looks something like this. Well, horizontal stretch and compression, the reason why we didn't learn about it when we were doing quadratics is because the shapes are kind of similar. And for quadratics specifically, if you found the vertical stretch or compression factor, you're actually finding or compensating for the horizontal stretch or compression factor as well. Because, well, let's think, a horizontal stretch. If I took our original and I stretched it horizontally, like took this point and pulled it out here and pulled it out here and pulled it out here and pulled it, and I kept stretching to the left and right only, it would just make the parabola look, well, exactly like it looks like if we had a vertical compression. And if I took the graph and I squeezed it horizontally and compressed it, if I took this parabola and I pushed everything inwards and made it skinnier, well, it would actually end up just looking like a vertical stretch. So the reason why we didn't learn about both of these last year is because they're kind of the same thing. For parabolas specifically, for other functions, they might look a little different, so it is important that we can know how to differentiate between the two. But I'll tell you exactly what I mean later in the lesson. The reason why there's bars around A and K is because, well, the sign, negative or positive, told you whether it was a reflection or not. And this just means absolute value. So what I'm asking you to do when you think about A and K, just ignore the sign, because that's the reflection, or not reflection, and just think about the magnitude or the number. So what's happening here? Well, whatever K is, if K is a number that's greater than 1, the number acting directly on X as a multiplier, then we're actually horizontally compressing the graph. And that would kind of be the opposite of what you were thinking about in terms of a value. If A is greater than 1, like if we had an A value of a parabola like 2 is a vertical stretch. But here I'm telling you it's a compression for K. It's actually the opposite. A vertical compression was when we had numbers like a half or a third or a quarter. But for a stretch, or for a horizontal, that would be a stretch. And the reason why is because much like D acted on X with the opposite sign, so does K. K acts in the opposite way you might think. If K is a whole number, you're actually taking the X's and dividing it by that whole number, or multiplying by a fraction. And I'll show you exactly what I mean as we move forward in the lesson. Here's a chart to summarize the effect. So again, if you had an A value, A is in front of the function, so like 2x squared, it would be a stretch by a factor of whatever that A value is, so 2 in that case. If we had a number between 0 and 1, so like 1/2 x squared, that'd be a vertical compression by a factor of 1 over A. If A was a half in this example, 1 over a half is 2. So a vertical compression by a factor of 2. This is the same as saying divide by 2 or multiply by a half. They mean the same thing. Just be careful in the way you word it. We want to word it in the way that always uses the factor as a whole number. So if the vertical compression factor is a half, the scale factor is a half, you would say it's a vertical compression by a factor of 2. Because you want to use your factor as a whole number. It makes more sense. It's logical that way. But I'll tell you exactly what I mean again as we move forward. Horizontal compressions act in the opposite way. If K, the number acting directly on X, is a number bigger than 1, we actually have a compression. And if it's a number between 0 and 1, we have a stretch horizontally. So here's an example. Here's a nice figure again, another triangle. Let's vertically stretch it and vertically compress it. Vertically stretch, vertically compress. Yes. So vertical stretch by a factor of 2. We're going to do what mathematically? Well, we're going to stretch it away from the middle. And the way we do that is we're actually multiplying the y values. And we're multiplying them by 2. So we take our 1, 2 point, and it would actually become 1, 4. We'd take our -1, -1 point, and it would become -1, -2, because we're multiplying the y by 2. We take our 0, 4 point, multiply the 0 by 2, stretching it, and it actually doesn't change. It becomes invariant. So we end up with a triangle that looks like this. This is just a stretched version of the same thing. So here we go. Let's go with pink. And there's our stretch. For our compression, here I'll use pencil. We're taking our y values, and if we're using multiplication, we're multiplied by 1/2 in this case, which is the same as dividing it by 2. So if we're compressing it, 1, 2, the point would become 1, 1. -1, -1 would become -1 and -1/2. And 4, 0, well, dividing by 2 or multiplying by 1/2, the y would actually stay the same. So that point's shared. And we end up with this triangle. So we've got a compressed triangle and a stretched triangle, vertically. What about horizontal? Well, horizontal stretch or compression. Let's take a look. Draw my figure. -4, -1. 0, 3. And -2, -3. And put my triangle together. Horizontal stretch by a factor of 2. All right, we've got our figure. 3 points, triangle. Horizontal stretch by a factor of 2. What are we doing here? Well, let's use pink. Horizontal stretch by a factor of 2. That's going to impact the x's if we're stretching by a factor of 2. That means we're taking those x values and we're multiplying by 2. So let's look at some x values. First point, 0, 3. If we're stretching it, 0 multiplied by 2 is 0. That point doesn't change. -4 times 2 would be -8. That would be -5, -6, -7, -8, be all the way over here. Y doesn't change. And -2, -3 multiplied the x by 2 would take us to -4, which would be this point right here. And if we connect these dots, we end up with our stretched graph. Sorry, let me turn the page here. And if I highlight in pink, see what we're doing here. There's our horizontal stretch. Horizontal compression would be multiplying the x values by 1/2 to compress it. So if we're multiplying by 1/2, that's like dividing by 2. -4, -1 is our point. If we divide it by 2, we get -2, -1. 0 would stay the same, and -2 would become -1. So we would stay the same. And we'd end up with a triangle in here. And there's our compression. So what are we doing here? Well, basically, if we think about everything in terms of multiplication, if we're stretching, we're multiplying x values by numbers bigger than 1. If we're compressing, we're multiplying by numbers less than 1, but bigger than 0. All right. So I kind of already described this. Your textbook uses a different convention than we use in the lessons. So when you're checking your answers to these questions, they might just have the reciprocal answer for compressions and stretches. So just be aware that saying multiplied by a half is basically the same thing as saying divide by 2. Writing everything in terms of multiplication makes things easier. So if we're saying the word compression, it's implying division. So if we say compressed by a factor of 2, it's just multiplying the y values by a half, or dividing by 2. Compression means division by 2. All right. So how come you didn't learn about horizontal stretches and compressions before? Well, because you can kind of take care of them just by finding vertical. And here's what I mean. Here's 2 graphs. The original is the absolute value of x. And the changed one is either a horizontal stretch or a vertical compression. And since we have 2 graphs here that look the exact same, we're actually going to solve for both. We're going to write an equation for this graph, assuming that this change is a vertical stretch or compression. And then we're going to do the same thing, assuming it's a horizontal stretch or compression, and show you 2 different equations that give you the same graph. So here's how we're going to do it. We are going to choose points on the parent function and find the corresponding point on the transform function by finding the point with the same x coordinate, and we're going to compare those values. And then we're going to use the general form of the equation, whether it be a f of x for vertical stretch or compression, or f at kx for a horizontal stretch or compression. So let's start with vertical. If it was a vertical stretch or compression, we'd have an a value, which is in front of the absolute value of x. So let's think about a point on our transform graph and solve for the a value. Well, let's pick a nice point. There's a point here that's a nice point. 8, 2. We're going to use that point. 8 is x, 2 is y. 2 for y, 8 for x. What's the absolute value of 8? 8. 8 times a is 8a. Divide both sides by 8, we get an a value. A is 1/4. We know the graph hasn't been shifted left, right, up, down, well, because the question didn't say it was, but also the starting point of the v of the absolute value shape didn't change from 0, 0. It's like the vertex didn't change if it was a parabola. So this graph has an a value of 1/4. So if we wanted to write the equation, we would say f of x is 1/4 absolute value of x. And in terms of a transformation, what transformation is that? Well, 1/4 for a is a vertical compression by a factor of 4. Why 4? Well, because we're compressing, which means division. We're dividing the y values by 4. That's how we get a point that should be way up here on our original to come all the way down here. We're dividing the y value by 4. What if it was a horizontal stretch or compression? Well, we'd do the same thing. We'd pick a point. Let's pick the same point. 8, 2. This time, we're going to write it as if it was a, oh, not a, sorry, k. And k would act directly on x inside the absolute value. So let's replace x and y. Y is 2. X is 8. K times 8 is 8k. The absolute value of 8k is 8k. Divide both sides by 8. We get 1/4 is k. What's that mean? Well, that means that the function, if we wrote it using horizontal stretch or compression, would be not 1/4 times the absolute value of x, but it would be the absolute value of 1/4 x. And k, being 1/4, would be what type of transformation? Well, think about the original. and it's being pulled this way, which would be a stretch. This would be a horizontal stretch by a factor of 4. How come? Well, because the x values would be 4 times as big than they should be. The original x was 2, and now it's 8. It's being stretched. It's being multiplied by 4. It doesn't look like x is being multiplied by 4, right? Because the x's are actually being quartered. But it's a quarter of the original x to get the same y. That's what the equation means. So, hold on. A quarter of x, a quarter of 8, would be 2 to get the original y, which would be 2. That's why the sign is opposite. So, horizontal stretch by a factor of 4 would be the transformation. So be very careful when working with fractions for vertical and horizontal stretch or compression. But a lot of practice with it will get you very comfortable. Thanks for watching, and I'll see you next time.